Alright guys, welcome to this page of the notes, and hopefully what you've recognized is actually this polynomial is exactly the same as the polynomial we just had on the last page of the notes. And that's because what I want to do is, finish this example problem and then show those of you who are actually taking this class with me how I'm going to ask you to report your final solutions. The idea is this: I'm essentially asking you to find all possible combinations of positive real, negative real, and imaginary zeros of the function. That's really what we're doing here. And so I want to show you how I'm going to ask you to do that if you're taking this class with me. And so we'll just keep going in the example problem that we've already worked on, which means I just need to get caught up. We already have done a whole bunch of work. Let me catch up to with where the rest of you guys are at. We've already said that the sign changes for the real positive roots are right here. There's 1, 2, 3, 4. And then I also had f of negative x. And again, this was on the last page. We already said that that comes out to x to the 6th minus 5x to the 5th plus 7x to the 4th plus x cubed plus 6x squared plus 2x plus 4. And we had 1, 2 sign changes there. All right, and so what we found then, sorry, hold up, I meant to slide it up a little bit. There we go. And so what we found on the previous page for this example problem was these two tables: the real positive roots were 4, that's the maximum, or less than that by an even amount. Well, that means any even number less than 4. So 4 would be, less than 4 by an even amount. 4 minus an even number. So that means I could have 2 or 0. And then the real negative roots, again, just rewriting what you guys already have in your notes on the previous page. We're just continuing that example problem. I found my polynomial by plugging in a domain value of negative x, doing a little bit of simple algebra to get this new polynomial, and I again count the number of sign changes, and I get 2. So the number of real negative roots at the most would be 2, but it could be less than that by an even amount, which in this case would leave me with the only option of 0. Now, here's how we're going to, what I'm going to ask you to do again if you're taking this class with me. The idea here is that you find, let me highlight it for you. You're going to find, in fact, I need to add that little bit there, right there. Just go and throw this in there. I probably should have written it and I didn't. You're going to find all. So I want you guys to find all the possible combinations. All possible combinations of positive real, negative real, or imaginary zeros of the function. And here's how I'm going to ask you to do it. In most cases, I will probably, for you, either in the homework or on the quiz, something like that, I'll have this table kind of set up for you, and you'll just need to fill in the table. So here we go. Let me draw a couple of lines down through there to separate our columns. And here we go. You're going to work your way systematically through the tables that you just created using Descartes' rule. And again, systematically, so that you don't forget anybody, here's what I would do. I'd start with the real positive roots. I'd start with that top number 4, right? So I could have, as a possibility, I could have 4 positive real roots. So I could have 4. Now, I'm going to match that up, right, with my negative real roots, which are also possibilities, right? So I could have 4 positive real roots, and I could have 2 negative real roots. That's a possibility, right? 4 positive roots and 2 negative roots. But I could have 4 positive roots and 0 negative real roots. Right? And that takes care of the 4 because I've already matched the 4 with the only 2 possibilities for negative real roots. So we go to the next one. I could have 2, right? 2 positive real roots, which would match up with 2 negative real roots. But I could also have 2 positive real roots and 0 negative real roots. And then 2 more. Again, we're just systematically working our way through the table to make sure I get every possible combination. Again, the directions said I want all possible combinations of positive real and negative real. So we are just systematically working our way through the tables we created to make sure I get all of those possibilities. And we're down to our last one, which is going to be this guy right here. I could have 0 positive roots and 2 negative, so 0 and 2. Or I could have 0 positive and 0 negative real roots, so 0 and 0. All right, so now we come to the last 2 columns. Now that I've got that, let me slide this up a little bit because the rest of the work is very, very simple. These are all possible combinations of positive real roots and negative real roots. The last 2 columns, piece of cake. We know from the fundamental theorem of algebra, you ready? Fundamental theorem of algebra tells me that because the degree of the polynomial is 6, I know that I must have 6 zeros. Those zeros could be real zeros, or they could be imaginary, or some combination of the two, but I must have 6 zeros. So here's what I know down here in my column. Every single one of these possibilities has to be equal to 6. So I've got to have 6 here, 6 here, 6 here, 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 and here, right? Every single one of these possible combinations must add up to 6 roots, because that's what the fundamental theorem of algebra says. It says I have to have 6 zeros, right? So every single one of these possible combinations must get me to 6. Right? But some of these don't add up to 6. Like, for example, this one right here, 2 and 2. That's only 4 zeros. The fundamental theorem of algebra tells me I have to have 6. This one here, 0 and 2. That only gets me 2 zeros. The fundamental theorem of algebra tells me I must have 6. So how do we make up the difference? Well, you make up the difference with imaginary zeros. So 4 plus 2, that's already 6. I don't need any imaginary. 4 plus 0 is 4, so I need 2 imaginary zeros to get me to 6. 2 and 2 is 4, so I need 2 imaginary zeros to get me to 6. 2 and 0 is 2, so I need 4 imaginary zeros to get me to 6. 0 and 2 is 2. Again, I need 4 imaginary zeros to get me to that grand total of 6. And 0 and 0 is nada. Zip, buckus, big old goose egg. You need all imaginary numbers, 6 imaginary numbers to get you that total. That's it. That's Descartes' rule. Use Descartes' rule to find all possible combinations of positive real, negative real, and imaginary zeros, knowing that for whatever your polynomial is, it must be equal to some total number, thanks to the fundamental theorem of algebra. That's Descartes' rule. I know it's not very tricky, and again, it doesn't really give me any information that I couldn't find by some other method or that's really important to any particular problem, but it's in your algebra book, and we need you to know how to do it, so that's why we're going over it. Head on over to the next page of the notes. We'll try another example problem, and I'll meet you there.